Hi, welcome to recap lecture number 1. The point of a recap lecture is not to teach you content for the first time, because this certainly will not be detailed enough to do that, but it is to review things that you should already know, just to make sure that you kind of brush up on them and remember what's going on. So the first topic of recap lecture number 1 is to think about limits. And I have on this first slide 4 different problems. I'm going to walk through these problems rather quickly with you. The first one is a limit as x approaches a particular value. Our first impulse should be to think about plugging that value in for x, and hopefully we realize fairly quickly that that isn't going to work out in this particular case because we get a 0 in the denominator. So what we're going to do instead, after we make sure that direct substitution isn't actually going to pay off for us, is to try some algebraic techniques. In this particular problem, the algebraic technique of factoring is what ends up working out. We factor the bottom by difference of squares. We factor the top because it's a quadratic that does factor. And in this case, we notice that one of the factors, x minus 2, is the same on the top and the bottom. And so this reduced expression is something that can be evaluated when x equals 2. So at this point, we can plug in the 2. And we find out that the limit is 11/4. What this would mean graphically is that this is a function, this original function is a function that has a removable discontinuity at 2. In other words, it has a hole at the point 2 comma 11/4. And so the limit exists because both sides of the function are approaching the value 11/4. In the next problem, we are going to utilize the idea of a conjugate. Once we indeed think about the fact that just plugging in 4 isn't going to be a thing that would work out for us. We always should check direct substitution first because it would be the easiest if it did happen to work. Here we're going to use the idea of a conjugate, which in this case is 3 plus the square root of the quantity x plus 5. So we multiply that on the top and the bottom, which would give us a difference of squares pattern on the top. And that is the reason why the conjugate is helpful to us. So up top we would have 9 minus parentheses x plus 5. On the bottom I would recopy both of those things that I already have. And then if you notice, something really lovely is going to happen up top, which is that the 9 and the minus 5 are going to make 4 minus x, which is exactly the opposite of x minus 4, which would give us the quantity of -1, and then we would plug the 4 in. So we'd have -1 over 3 plus square root of x plus 5, which will limit as x approaches 4. Sorry, my handwriting is so atrocious on this tablet. And you plug in the 4, and you get an answer of -1/6. Okay? The next problem makes use of the idea, actually just like the memorized fact more like, that the limit as something approaches 0 of the sign of that thing over that thing, that quantity equals 1. And this comes out of one of our first lessons. We were discussing the idea of local linearity. And we were discussing the fact that the sine curve, although very different from the graph of y equals x in most places, when you're looking near the origin, near 0, the function y equals x and the function y equals sine of x are actually very similar, close to the origin. And so their quotient is close to 1 because those two functions, the blue line and the black curve that I kind of doodled there, actually are really remarkably similar in that particular area. Only near 0, not everywhere. So here we have something that's sort of reminiscent of that limit, and what we choose to do to make it kind of match the form is to multiply by 5/5. Now the value in this is that we can kind of smush things around a bit to make it fit the limit that I wrote in purple pen up there. So let's say we have the limit as x approaches 0, and we take this 5 on the top and 3 that's on the bottom, and we kind of split that off of the rest of the product. And then we have sine of 5x over, and then the thing that we have left is a 5 and an x. Look at that. And there's a property of limits that says if we have a multiplier, we can pull that out. And then this part's limit, as discussed up here, is 1, because if x is approaching 0, that's what we really needed there. And so the part in parentheses would, along with the limit statement, would equal 0. excuse me, the part in parentheses along with the limit statement would equal 1, I meant to say, and 1 times 5/3 is 5/3. All right, then underneath that, I have this piecewise function, and people seem to freak out a little bit when they see piecewise functions, and so I would say a key to piecewise functions is just staying calm. So if you've read this question, you'll notice that it asks us to find a and b, and we want the limit to exist at 2, and we want it to be equal to f at 2. So the function's value at 2, based on that middle line there, is 3. So we know this function contains the point 2 comma 3. And we want that limit as x approaches 3, as x approaches 2, we want it to be 3. So that means that as we come from the left, which is this portion, oh my gosh, as we come from the left, we want that left-hand limit to equal 3. And as we come from the right, we want that right-hand limit, which is from that branch, to also equal 3. So in other words, I just need to plug in 2 into both branches. So a plus b times x equals 2 has to be 3, and b minus a times x equals 2 has to equal 3. Okay, and if I solve that resulting system of equations, we should get that a equals negative 1/3 and b equals 5/3. Now I'm not going to go through the solving of the system of equations necessarily, because I don't think that's part of what we need to necessarily be reviewing at this point, but if that's something you think you should practice, then certainly practice it. I would like you to pause your own device right now and try question number 5, which reviews one-sided as well as overall limits with this piecewise function, and then start the video again once you have your answers. Okay, let's see how you did. Right here are my solutions. Right here. Oh, I have a little bit of a typo. Okay, sorry, some of my writing seemed to have slid around on the screen. So these are the answers that I have, and make sure that you remember a few little details that I'll highlight. The plus means you're looking from the right only. It's a one-sided limit. The minus following the number means you're looking at a left-sided limit. In order for an overall limit to exist, the right and left-sided limits have to be identical and have to be an actual finite number, not something that's going to infinity or something like that. I think the rest of it should be clear. You end up using the picture sometimes. You end up using these definitions of the different pieces in terms of their equations at times. If any of this is something you got incorrect, then you certainly do need to have a little conversation with me tomorrow, okay, and make sure that you're clear on that. The next thing that one of the reasons that we study limits is because limits are behind the definition of the derivative as well as the integral, as we saw later on in class. But this is something we talked about early on first semester. So all of these could be referred to as the limit definition of the derivative, which means that this expression here that I have would be equivalent to f prime of x. I didn't write that over here. I should have done that. This first one is the one that we tend to use most of the time. The second one is the one that is actually programmed into your calculator when you use mderiv. And I referred to this earlier in the year as the symmetric definition of the derivative, because you can see from the parts that are up here, what you're doing is, say you have a curve and you're using this definition of the derivative. You're saying, okay, I want the derivative here. What I'm going to do is go a little bit to the right and a little bit to the left of that location. So this is like x, and this is x plus h, and this is x minus h. And I'm looking at the slope of that line connecting those 2 points. And then by taking the limit, it's forcing those 2 points that were initially green on my very sloppy picture. It's forcing those 2 points to slide together to be infinitely close. And then that line that I initially drew becomes a tangent line. I could have done that so much better than I did. Maybe I'll try that one more time. Well, I'm talking about something else maybe, so this video doesn't get immensely long. So here's our function. Here's the x. Here are the other 2 points. This is h units this way. This is h units this way, and we have this line. And then as this point and this point slide closer together, they become this tangent line, which is indeed the idea behind this as well. But in the way of writing it here in this symmetric definition, it's because you're going to the right and to the left rather than, say, just to the right. This is what your textbook, what Mr. Larson refers to as the alternate definition of the derivative. And what it's telling you is f prime at a value c. And what we discussed in class when we went over this way a long time ago is that if I wanted to find, say, f prime of 5, if that were the question, and all I have is the limit definition of the derivative, I could use the traditional definition, the typical definition, find the equation for the derivative, and then substitute in 5. Or I could use this alternate definition of the derivative, and it will automatically give me f prime at 5. I don't have that extra step of like finding a generic f prime and then substituting in a value. It's not really a huge difference, but it's like one step more efficient. So something that you should notice here is that this says as x approaches c, this says as h approaches 0. This is how you find slope. That's Algebra 1 slope right in there. Okay, so understand that that's what all of these are actually based on, is the formula for slope from Algebra 1. Okay, so something else that I'd like to point out is just reminding you when things are not differentiable, when functions are not differentiable. This is not to be confused with continuity. So a function certainly can be continuous at a given location, yet not be differentiable at that same location. So there's some overlap, certainly, like something that does have a discontinuity is neither continuous nor differentiable. Right, something like this can have a derivative all through here and all through here, but at the place where this jump happens, no can do. There's no derivative at that spot. This guy, the cusp, is the one that I think of as how I draw birds. Oops, I can't really draw very well. That's this, okay? So this point down here is called the cusp. Now this green function is continuous all through this part that I drew. So all through its, what I'm guessing is its domain. It's even continuous right here. However, this function is not differentiable right there at that dot, okay, because it's pointy. Another thing that would be pointy is if we had a corner. So a traditional example is the absolute value function. Okay, and so this function also is continuous all through here. That is true, but it is not differentiable right here. And if you have a function like, I don't know why I'm drawing so badly with this today. The cube root function, like that. There's a spot on the cube root function where the tangent line would be absolutely vertical. And I'm not drawing it very well, but if you look at the graph of this on your calculator, you'll probably get a better picture. Definitely get a better picture. But the cube root function has a spot right in here where the tangent line becomes vertical and the slope would be undefined. And slope is the derivative, okay? Derivative is slope. So if the slope is undefined, that means the derivative is undefined. This is a good sentence to remember. Differentiability, if something is differentiable, it has to be continuous because of this situation. So if I know a function is differentiable, it has to be continuous. The other way around with those two words, not so much the case. All right, something else that I just wanted to hit on very quickly is average versus instantaneous rates of change. An average rate of change is when you would take two different points. Like in this picture, I just clipped this off of this website. It's just a little demo about showing the height of a balloon at different points. So if you look at this on this website, you'll see that there's a slider for time, and this balloon goes up and down, and then the graph is a record of the pattern of the balloon's height. So that was just a cute little picture anyway. But if you were to take this point and this point, you could connect the dots and find the slope of that secant line, and that would be the average rate of change in the balloon's height. However, if you were more interested in how fast is the balloon's height changing at this point, what you would need is the actual slope of the tangent line. So this is all about slope of the secant line versus slope of the tangent line. The average rate of change is the secant line slope Oh, I really do not know. My arm must be bumping something. This is maybe the worst recording I've ever made, you guys. Aren't you lucky to be able to be listening to it? I'm having all these little technical glitchy issues, and the pen is crazy. My arm is bumping something on the tablet, on the toolbox down there. Okay, so the average rate of change is the secant line slope. I wish you could see how I'm holding my hand right now in order to write this. There you go. Secant line slope, and then the instantaneous rate of change is the tangent line slope, which is the derivative. Derivatives tell you the tangent line slope. All right, another thing that you should just remember is the good old mean value theorem for derivatives. Okay, we have abbreviated this before, mean value theorem for derivatives. There's also a mean value theorem for integrals. Rolle's theorem is a special case of the mean value theorem. So if you recall Rolle's theorem, where we had the two Rollos right across from each other, which meant that the endpoints had the same y coordinate, and then you have something in between that's continuous and differentiable. And what Rolle's theorem said is there has to be at least one spot where the tangent line slope is 0. And in my picture, there's 2 places. Okay, but there has to be at least one place. The mean value theorem is this same theorem. This is my picture for Rolle's theorem. The mean value theorem for derivatives says, okay, you have 2 points. They don't have to be at the same level. It actually doesn't mention that, but that's how it would start in the drawing. And you have something that's continuous and differentiable. And the mean value theorem for derivatives says, hey, find that secant line slope. Pretend that's a straight line, guys. And there has to be a place, at least one place, somewhere in between these 2 endpoints, where the slope of that secant line and the slope of that tangent line are the same, so that those are parallel. Okay, so if you look over at the words here, these are the words for the mean value theorem. We have a continuous function on the closed interval. It has to be differentiable on the open interval. This is an open interval because at the endpoint, we're not really sure what the tangent line would look like. That's kind of ambiguous. So there has to be a place somewhere in the interval where the slope of the tangent line at that value c, so slope of tangent line at c, has to be equivalent to, and then what's this? What you said it was the slope of the secant line. And it's the secant line that contains the endpoints, so from okay, so the slope of the secant line has to equal the slope of the tangent line for at least one tangent line, maybe in more than one place. That's mean value theorem. Okay, derivative rules I think we've used exhaustively, so hopefully you are not exhausted, but do know them. The power rule, the product rule, quotient rule, chain rule. A lot of questions that I have seen in old free response questions especially, it is helpful to be able to write the chain rule in this form. So if you have a function like g inside of another function like f, they hopefully recognize that chain rule is applied when you have compositions of functions, which this is. And so to say the chain rule symbolically can be helpful because sometimes you have data that's in a chart rather than, say, an equation. So this would allow you to pull data off of a table pretty easily. So remember that in the chain rule, you take the derivative of the outside, keep the inside, and then multiply by the derivative of the inside. Okay, so I would definitely just I guess I wrote this on your notes already. It's really good to be able to write it out in that kind of format. All right, another thing we talked about around this point in the school year that I was flipping through old notes in making this, one of the things we talked about was being able to draw a graph of the derivative given an original function. So I don't know if this is exactly, I think this is most likely to be tested multiple choice in the way that I'm showing you right here. So if this is your original function, which one of these could be the graph of the derivative? I see that as a multiple choice question, not a free response so very much. And certainly I don't think there's going to be a place where you're going to need to actually draw the graph of the derivative. That was just there because I thought it was a good way for you to think about questions like the first one. So I would like you to just pause the video again and then come back in a minute. We'll look at the answers to these two. Okay, so these are my answers. This graph is the one that was in the upper right-hand corner, so I hope that you picked that one. And then here's a sketch of what your derivative graph should look like. To determine that, I just would look at the places that are most important, such as right here. This is a point where the tangent line would be horizontal, so the derivative would be 0. So that would translate to a point right here in the derivative graph. That's the same for this location at 2 and for the location at 3. And then I would start thinking about the signs of the derivative. So here, the function is increasing, so the derivative would have to be positive, so this must be coming in from this side. Here, the derivative would be negative, 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 all the way down to here, so I know my graph has to go down below, something like this. Then in here, my original function is increasing, so that means positive derivative values. And then over here, the derivative is decreasing, so I'd have to have negative values on my derivative graph. So something along those lines. And the same kind of thinking would help me pick out the multiple choice question that I talked about right there. Okay? All right. The very last thing for today is to remember the intermediate value theorem. And the intermediate value theorem is really well named. Think about the fact of the word intermediate meaning something in between. So you have to start out with an idea that the function is continuous. So start out with that. So if a function is continuous on some interval, call it a to b, and you have a value m that's in between a and b. So if a function is continuous and m is in between. So I'm going to choose to write it because it's the way my picture goes, that f of a is the smallest and f of b is the biggest. But these inequality signs could go exactly in the reverse if that were applicable. So if those two conditions are met, then it has to be true. Then there exists, that's a symbol for there exists, at least one value, let's call that value C, and it's in between A and B. Could be more than one, but at least one, such that at that x coordinate of C, the function value at C is that middle value m. Okay? So if I have a function that goes from here to here in a continuous way, these are the two y coordinates. I pick any y coordinate in between those two. There has to be at least one place where there's an x value that gives me that y value. And in this case, there's several. There's another x value that gives me that y value. Another x value that gives me that y value. The hard thing that people have, I think the hard thing, is not so much the idea of this theorem, it's being able to put it into words. And I would strongly advise that you just memorize this sentence, basically. Understanding the idea, very important. And people tend to, my students in the past, and I think you guys as well, understand this idea, but to try to get that sentence out on paper when you're in a timed testing situation can be difficult. So, first of all, understand the idea. And then secondly, just try to have some structure to your thoughts on it. Okay? Thank you so much for going through this, and we will have a lot of fun with these topics in class the next couple of days. Thanks.